There are
Okay.
two major parts to it, like what I'm going to cover today, which is statistics. On statistics
Okay.
side, I'll be going ahead with how do you approach a statistical testing, kind of an A/B
Great.
test kind of a thing. How do you
Okay.
basically do a significance testing? And
Okay.
there's a
Okay.
standard pattern to significance testing. So I will
Oh, I
explain
see.
one, and then there is some a link that I have that has
Okay.
details to all the other statistical testing methods.
And
But
how are the things?
yeah,
How are the things in US? How are the things in US? How is the situation there?
the situation is getting better, but it's not any good as of now. Like as you can see
Okay.
from my hair,
Okay.
the salons are all closed and things are going really
Okay.
bad in that sense.
Really.
So I apologize for that, but then the situations are
So
like that.
so lockdown is there for almost 2 months in the
Lockdown has
US.
been there since March, second week March.
March. Oh, I see. So you've been working, work from home since March only, or
Yeah,
before that?
yes.
Since
Adobe
March
was one
itself.
of the very first companies to go on a lockdown. So since then, we have been working from home only.
Oh, I see. Okay, okay. So any specific project you are working right now, or in the Adobe there?
Yeah, so right now in Adobe, there are multiple projects that I have under me. One of
Okay,
the very interesting ones are a causal analysis.
okay,
Basically, we are
okay,
trying to build a causal model, and one
okay,
more is fraud solutions. Basically, we are trying to see if we can catch the fraudsters who are trying to get into the system.
okay,
And
okay.
basically, that's like a classification model.
Great, great, great. Okay. So, Teresa, shall we start the session?
Yes, sir. You initiate it. Yes, sir.
Yeah. We will start. So, good morning, all of you. So, it's a very wonderful session that we have arranged, and we are really delighted to have Mr. Atharva. He has done his engineering from St. Francis here in Mumbai University, and he has got a wide experience in the software industry. And he has worked earlier in the Bangalore in an industry, software industry, and then he has switched over to US. And he has been working in the Adobe as a senior data scientist currently. And we are really fortunate to have with us the distinguished personality in the field of computer science, specifically in the data science. And I'm sure that the all the participants all having in the faculties in the different colleges and Mumbai University, they will be benefited, and they will definitely get a different perspective in the data science, how data science will be applicable. And so I'm really sure that you will have a wonderful session, and you will get the application where the data science is being used in the industry. So I don't think we can have a much better person than Mr. Atharva, who has been working in the same field for so many years. And so I'll not waste much of the time of the participants, and I will directly hand over the session to Atharva to start the session on data science applications. Over to Atharva.
Thanks a lot, Trivedi sir. Um, I'll be stopping the video now, and let me start sharing the screen. So screen one, share. Please let me know once you're able to see my screen so I can go ahead and
Your
start.
screen is visible perfectly.
Awesome. So
Great.
just 1 second.
Go ahead.
Yeah. So that's you're able to see the screen, right? Perfect.
Yeah.
So let me
It's
start.
visible. Yeah.
Whenever we go in the field of industry today, anywhere, and when I say industry, I mean any industry, this is literally the principle everyone is using today. Like in God we trust, everyone else bring your own data. And that is the very specific reason behind that is data never lies. You always know what's the exact situation is and what's the exact situation going to be if you look at the data properly. So let's go ahead and start the session. And as we go ahead, I'll explain you even in more detail. So as Trivedi sir explained, I will give this really quick. I did my B from in information technology from St. Francis, which was in the Mumbai University. I worked for around 2.5 years as a decision scientist with a company called Sigma in Bangalore. After that, working for 2.5 years, I decided to pursue my higher studies in data science since I started liking the overall field and the kind of work we do in there. So I decided to go ahead pursue my MS in data science from School of Informatics and Computing, which is part of Indiana University. And then in April 2018, I joined Adobe, and I've been with them since. Now, a lot of people have a question like, what does a data scientist do, or what is data science? So data science typically lies on three different pillars. The one being maths and statistics, because that is what you need basically to understand what your data is saying. Second thing is technology. Now, obviously, once you have data, it's not always in the best usable format. Sometimes your data needs to be aggregated. Sometimes your data needs to be cleaned. There has to be a lot of transformations that happen. Sometimes the data that you have comes in literally text files and you have to extract the information you need from there. And that's where the technology comes into picture. And once these two are there, you still need something called as perspective, because you need to understand what your business is before you put anything on top of it. For a very simple example, if you have a retail industry that you're trying to solve a problem for, unless you understand how a retail industry works, you'll never be able to solve the problem. And the problem that comes in a retail industry where you sell something to a customer and you're done, that is a very different problem than a subscription based industry, where you have, once you sell a customer, you have to make sure that you keep billing the customer every month and the customer doesn't leave you. So that part is basically your business domain. And when you have all those three parts together, you can be solving problems end to end, and that's the job of a data scientist. Now, I'm not saying that is the only thing that you have to do. Obviously, a data scientist would not know everything. So there are a lot of SMEs that we continuously interact with. We have statisticians in the industry, we have DevOps, we have computer scientists, we have are actually business experts. And those subject matter experts we always pull into the picture whenever we need them. But as a data scientist, these three things are something that you will do regularly on everyday basis. And that is the core skill set a data scientist needs to have. So let's go to the next slide. Yep. So as I said, right, let me give you a little bit of example of how my daily job, my everyday looks like in the industry. So as a data scientist, my literally role is problem solving. Whenever we get to a situation where we see that, okay, the sales are going down, or it looks like the sales might go down, or the churn has increased. Churn is basically a customer leaving you. A customer that has been buying your subscriptions over the past suddenly decides to cancel, and that is called churn. And what happens in that case is basically we get a problem from business, and most of the times we get like literally a one-line sentence from the business saying, hey, this is happening, help us with it. And then we have to sit down with the business, define a problem, that what is exactly happening, what type of customers are leaving us, where is the problem, who's doing this, why that particular thing is happening. And we formulate an entire problem set saying, okay, this is what we need to do. After that comes your factor map. Factor map is literally your brainstorming. That is basically you figure out what could be impacting your business, and here you don't worry about whether you have the data or not. What would you do about it? Nothing. Here you just list down everything that might impact your problem. Once you have that list of 10, 50, or even 500 things, after that you see out of those things how many things you could gather data for, how many things could you actually measure, how many things are not measurable. And then based on that, whatever amount of information you have, you either set up experiments to gather the data, or you use your already existing data, you clean it, you prep it, you make sure that entire data is in good consumable format, because all your analysis is only as good as your data. If your data is not good, your analysis is never going to be good. So this is one step that we'll really spend a lot of time on. After that comes your exploratory data analysis. I'll not go a lot deep into it, because going ahead, there's going to be another slide where we'll be talking about what exploratory data analysis is. But this is basically you just look at your data, look at relationship between your various factors that you figured out in your step 2. You eliminate the obvious factors. So by obvious factors, I mean if you have two columns, one says what's your birth date and the other says what your age is, doesn't make sense to involve both of them in your analysis. So that's a kind of an example that I gave, but there could be a lot of such things. So you remove the obvious columns and you pick a starting point. When I say you decide either you use a supervised or an unsupervised clustering algorithm or a classification or regression algorithm, and I'll talk about these in detail ahead. But this is basically you just decide what your starting point would be. It's very possible that the first model you build is going to be useless, and you might have to build something else. But it just gives you a direction to start from. Next part is applying the actual ML algorithm. And applying that machine learning algorithm is literally 5 to 10% of the job. The main job is done till here when you decide which algorithm you need to use. You pick one, and your choice is what matters. Once you choose an algorithm that needs to be applied, there are thousands of packages that you get online, and you can use it. Just plug it in, and you can have your model ready. Next thing is you pick actionable insights from your model. Now, why does so much stress on actionable? Because once you understand something, learn something from your model, it has to be converted into some kind of a business action. Suppose you understand from your model that having a competitor store near your store causes problem. That's not going to be an actionable insight directly, because you cannot go and close on competitor stores. So it has to be something like, oh, if I have these 10 products, my sales are generally higher than if I have these 10 brands. That kind of insight is an actionable insight, something that you can take an action on. If I'm doing some analysis on human resource data for a company, and I come up with an action with an insight saying, oh, if you have employees of one particular race, they generally leave your company earlier than others. So don't hire that particular race. It's going to be an illegal thing to do. So that's not kind of an actionable insight. And that is where knowing your business, knowing your constraint is more important. And the last thing is obviously you have to measure the impact of your actions, because unless and until you see whether whatever model you put in action has gained the necessary impact, you'll never know if the model was actually good or not. And if it was not good, going ahead, you have to take care of that feedback, and then you have to make sure that you take care of it in your next models that are going to come. So any questions still here? Should I move ahead? Are you guys able to hear me? I'm really sorry you're breaking up. I couldn't hear you at all.
Yeah, Atharva, you can go ahead. You can go ahead. If any queries are there, they will be in the. Hello.
Okay, I heard I can go ahead, right?
Hello? Yeah.
So you continue. You continue your explanation. If at the end we'll take questions.
Okay, awesome. So let's go to the next slide. The kind of problems that we generally face in data science. So the first kind of problems are descriptive. This is where a CEO of a company probably wants to know how the business is doing, or what is my current situation, how are my stores performing today. Now you can't give a CEO a 500 lines document saying, oh, this store is doing this store is doing this, and he can't go through, or she can't go through a 5,000 lines document to understand how the business is doing. They need to know on one screen and within a few seconds, in a glance, how the business is doing. You need to and the analysts like us have to come up with different KPIs, different performance models to bring that business performance up and pick up any anomalies that are there and highlight those. So that's part of your descriptive analysis, and it has a very good overlap with exploratory as well. Like descriptive analytics is basically where you build the dashboard, you build the KPIs. But exploratory analytics is when you find those anomalies, you figure out where those anomalies correlated, or what does those anomalies correlated with. For example, if you see that on one particular day there was a sudden spike in sales, you might be seeing that in the descriptive analytics. But exploratory analytics is telling your business that, oh, you had these 2 promos running during that day, and that caused that spike. That's your exploratory analysis. On top of that, there's inferential, where you actually run different kind of tests, basically. For example, if you want to change the layout of your stores. Now, I'm doing this with respect to DMart in mind, because that's one thing everyone is familiar with, what a DMart is. So every DMart has a certain pattern. You go in, you have the counters, you have different things, you have different groceries at one place, you have apparel at another place. Now, what if I want to change that? What if I want to run some tests and see if I change the layout, how will the customers react to it? That is my inferential analytics, that I perform an experiment and then see what I can infer from it. Next type is predictive. Predictive is basically, I know that for the past 10 years, my sales have been like this. I need to know how my sales are going to be for the next quarter. That is where the predictive analytics comes into picture. And predictive analytics means basically you are trying to forecast your whatever patterns you have been seeing over the past few years onto the next few months or years, even if needed. And that also includes classification. That example would be as how many of the customers that I have today are at risk of going to some other store. That is basically your classification, which also comes as a part of predictive analytics because you're predicting their behavior. And next is causal. Causal is basically, oh, my sales are going down, and what is causing that dip? Is it the particular brand I changed? Is it the competitors, or is it the global economy index? What is it? And how do I test for it? So the causal analysis is basically when you figure out something where you have an X that's driving your Y, but your Y doesn't drive your X. Basically, it's not a correlation, it's a one-way causation, one-way driver and driven kind of a relationship. And the first three that you have, they come typically under your statistics part, and these two are generally under your machine learning part. And again, as I mentioned before, statistics and machine learning are not very different. Machine learning is 90% built on top of statistics, so there's a very thin line in between them, but this is generally the convention of going about it. Now let's come to hypothesis testing. I just, when I was looking at all the participants, I saw that there are some PhDs with us today in this session, and I'm pretty sure you are familiar with conducting experiments, because for most of the researchers in science, where it comes to physics, biology, chemistry, a lot of PhDs are built on experimentation. And that is where the entire hypothesis testing or A/B testing concept comes in. Why do we need to do this? Because once we have a theory that a certain thing works a certain way, there has to be some proof for it. The experiment has been conducted, the data has been collected, and now we need to test that, okay, this whatever sample that we have collected the data for, that sample properly represents what your theory is for the entire population. And that's where your hypothesis testing comes into picture. And there are multiple methods of doing that. There is something called as a z-test, there's something called as a t-test, there's ANOVA, and these all tests have their own fit into the statistics. For example, okay, let me first talk about what exactly statistical testing process is, and then we can go ahead and talk about when a z-test is to be used. So as we discussed, first is define the problem that we already spoke about. Second is defining the null hypothesis. Now I'm going to run you through an example, so that will make things even clearer for you. But a null hypothesis is basically that one exact theory that you're trying to test. That theory could be anything. That changing the layout of my shops increases the average number of people who are buying a particular brand. That could be a null hypothesis. Or it could be anything of that sort, where you basically that you want to measure through the experiment. The next is calculating the test statistic. Again, right now this will not make a lot of sense, but on the next few slides that will be very clear on what a test statistic is. but that is basically the way you are measuring your spread of your data. And once that is done, you find the probability of your null hypothesis being accepted or rejected based on the test statistic. And that will tell you a good direction of whether your null hypothesis can be accepted or not. So let's go in the next step and see when a z-test works. So when you're working with means, basically, so where you have a sample and you know kind of the population mean for your sample, that is where your z-test would start, will make sense. Then the sample size has to be greater than 100, or at least the population has to be normally distributed. Now, why this greater than 100 number? That is because of a theorem called as a central limit theorem. The central limit theorem, I mean, we'll not get into the details of it, but let me give you a very vague idea on it. It basically says that if your sample size is large in number, it's okay to assume normality. So if it's smaller, you have to check for the normality and make sure that it's normal. And if it's not smaller, if it's more than 100, then you can assume normality and use z-test directly. If this condition is not valid, that is where t-test comes into the picture. But we're not talking of t-test right now, and in interest of time, and we will right now keep our focus on z-test. And second is that we know the population standard deviation. Again, this is something that you generally know when you're conducting experiments, and based on that, you can go ahead and decide whether the sigma is a good assumption or not. And the next is working with ratios. Like instead of knowing the means, we know like, okay, 10% of my population is of this height and the remaining is of some other height. And then I have some null hypothesis based on that. And if you're working with ratios, then this particular thing, like your n into the ratio should be greater than 10, and your n into 1 minus probability of that happening should also be greater than 10. This basically is just to make sure that your sample size is large enough and it's normally distributed. So let's go to the example. Now here is our example. Here's our problem statement. A student is trying to see that how many professors that he has or she has in her college are how many of them they use memes. So they conduct an experiment. They go from class to class every time a professor uses a new meme, they write it down. They make a note of it. And after a year of classes, that student has recorded a certain meme count, which is in every class, each professor, how many number of memes those professors used. Now what I want to know is that on an average, a professor knows 3 memes. That's basically what the student wants to validate. Now, if you look at data, it looks like, yeah, most of the times it's above 3, it's very less, it's below 3. But that's not a good way to just look at it and then say that, oh yeah, that works fine. So you have to actually do some statistical significance testing and then see if this makes sense or not. So how do we do that? As we said, we build the problem, we defined a null hypothesis that says that an average professor knows 3 memes. Now this is a null hypothesis. And if this is a null hypothesis, the alternate hypothesis means that an average professor does not know 3 memes. That means it could be either less than 3 or it could be greater than 3. When we have this kind of a null and alternate hypothesis, where the null hypothesis says exactly 3, and the alternate hypothesis says either more than that mean or either less than that mean. That means it's a two-tailed test. Basically, both the tails of the bell curve is something that you have to understand. And yeah, I'll explain it in the next part. Why is it called two-tailed test? But let's talk about the Z statistic first. Now, what is a Z statistic? A Z statistic is basically when you fit a normal curve, a standard normal curve to your data. The Z statistic says that where does your mean lies? Like mu equal to 3, where will that lie on the normal curve? Now that what you see here in the distribution plot is a standard normal bell curve, which basically means that it's a bell curve that has mean equal to 0 and standard deviation of 1. And by this formula that we have here, x bar minus mu, basically the mean for null hypothesis divided by your standard deviation divided by your root n. If you work this out, your x bar is basically your mean of all your samples. Your mu0 is your based on your null hypothesis, so that is 3. Your sigma is what we have seen here, that we have decided that sigma equal to 2 is a reasonable value for standard deviation. And underscore of n is basically the number of samples here and a square root of that. And if we work this out, let me pull R up over here. So this is R, and this is the formula. Okay, before that, as we decided over here in our previous thing, that we have to check if the data is normally distributed. Now, how are we going to do that? So let's start by pulling. Are you able to see the RStudio properly, everyone?
Yes, but if you can increase the font size, it will be better.
Let me check if I can do that.
Zoom in over there, na? Zoom in the previous one.
No, I tried that last time. Session. There should be a preferences. Let me do this.
That's better. Show it in notepad.
Yep, I'm just waiting for it to start. A lot of codes are open there. Okay, there we go. Is it visible now?
Yes, go ahead.
Okay, so the first line is basically to read the literally read the data, and QQ norm or QQ line is basically where we can check if the data is normal or not. So let's see how do we do that. So in your R, what you just do is first you read the data. Let me clear the previous session. And I just to select this, Control Enter. So once you run it and it's completed running, you will see a normal QQ plot here. And this is from the previous one. Let me clear this one as well. So this is your X that you just read over here. And a normal QQ plot looks like this. And in a QQ plot, it's a standard function of R. What we should see is that all the points that you plot should look like a straight line. If all your points over here are on a straight line, that means your data is normally distributed. So let's check that. If you pull a QQ line, now you see that all the points that we have, they are reasonably near the line that you have for normal. And that is why it's okay to assume that our data is normally distributed. So let's go on to the next part. N is the length of X, as I said. To calculate Z statistics, this was our formula. Mean of X bar minus 3 is our null hypothesis. 2 was our sigma, and divided by square root of n. So once we do this, we can understand what the Z statistic would be. Z stat not found because n was not there. So now we have our n as 10, and then we'll have our Z statistics as 2.37. So now that we know that our Z statistic is 2.37, let's understand what this means, because this is really very important. So if you see this, Our Z statistic was 2.37, which was this red line that you see here. Is everyone able to see properly what red line I'm talking about? This vertical red line that you see here, that is your Z statistic. And this Z statistic for mu equal to 3 means your probability of an average professor knowing three memes is going to be the area between these two red lines. So the area between these two red lines is the area where the professor knows is the probability of the professor knowing exactly 3 memes. So if you need to know, if you want to know if the professor knows more than 3 memes, then it's going to be the area between the curves at the right of this red line, which on the positive side, and at the left of this red line on the negative side. Now, how do I get these areas? Because this is a cumulative density function. Since it's a normal curve, if you use a cumulative density function, you can find this exact areas. And to do that, what we would do is go back to R again and use the formula of a cumulative distribution function, where we pass the Z as a normal of a standard normal curve of 0, 1. 0 is your mean, 1 is your standard deviation, and the Z stat that we calculated. And we do this because we have to subtract it from 1. So if we do this, cannot find city. Okay, because we didn't do library. And we do this. Objects are not found. Okay, because we didn't do this and this. So as we see, I'm sorry, the P1 is 0.017, which is basically 1.7%. So the probability that the professor knows exactly 3 memes is 1.7%, which is pretty small in this case. But what if we want to know that a professor knows more than 3 memes? What do we do in that case? So let's go back to R. This thing. Now, to know that the professor knows exactly 3 memes, we just need to know the probability of this tiny area over here. And this tiny area, if we need to know the probability, we just need the CDF of this particular small function. And that particular small area, if we need the area under that, we can just do a CDF of Z, Z stat. That way we'll get that one. So let's see what does that give us. So if you see the P3 over here, 0.9911, that means there is a 99% probability that the professor might know more than 3 memes. And that is how you come to a conclusion on your hypothesis, whether your hypothesis could be a true or it can be negated. Now, that is generally not where we stop. There's another concept of a thing called confidence interval, that how confident we are about this particular probability that we have built up. But in interest of time, I'm not covering that right now. But that is something which we use to go ahead generally in the case of biology or in case of very sensitive experiments, we go ahead and we use the concept of confidence interval as well and make sure that we are at least 95 to 98% confident that our value remains between that range. So that's your general method of going about an A/B test or a hypothesis testing. And this is whether different tests that we do. In Z-test and T-test, we have both 1 sample and 2 sample Z-test or T-tests. This is, as I mentioned, right, the test for knowing exactly three memes was a double-ended test where we wanted to know the area under both the tails. The probability of finding more than a professor knowing more than three memes was a single-ended test where we wanted to know exactly what the area under one particular tail of the bell curve. And ANOVA is something different, which is generally used in cases where you have more than one sample and you want to see if those samples are different. Now, there are also some cases where we don't know anything about the mean or median of the samples. We just have two samples and we don't know anything about the population, and we need to make some inferences about that. In that case, there is also an option of a non-parametric test called Wilcoxon rank test, which is one of the very famous non-parametric tests. And there are some other non-parametric tests also, but this is one of the most used. And if you want to know more about these in detail, there's a website called Khan Academy, which is very well known for statistics. And you can feel free to join it, and it has some free courses that talk in detail about all of these. Now, hypothesis testing was a entire class for me during my master's, like an entire 3 credit course across a semester. So I can't really go through every part of it in this session, but these are some of the major testings that you might need to learn to actually understand what hypothesis testing is. With that, let's move on to our next topic for today, that is machine learning. So machine learning also, I'll be able to give you an example of what machine learning is, what are some common pitfalls that we are supposed to avoid in while working with machine learning and building a model. And we will go in detail with the linear regression and what all do we need to understand before we decide to go ahead and apply linear regression to any particular data. So having that said, let's get started with it. So why do we need machine learning? Because everything that we need to know from the data is not going to be readily available, and it's not going to be available in the way we want it to be. For example, if you need to know how a customer is going to react based on how your previous customers have reacted, that is not going to be readily available. You'll have to understand the patterns in a data, and then based on those patterns, you'll have to score the new customer that's coming in. That is where we need machine learning. Now, as I said before, we were talking about supervised versus unsupervised learnings. Now, what is a supervised learning and what is an unsupervised learning? Basically, the only question you need to ask yourself is, do you have a class variable? A class variable is the variable that you want to predict or that you want to classify based on. For example, if I want to predict my sales, the sales is my class variable. If I want to see if a customer is at risk based on the previous customers who have left my shop or who have left coming to my shop, whether the customer has left me or not left me, that particular thing is a class variable. Then what is an unsupervised learning? As it's very clear from the description, there will not be any class variable available there. For example, I have a lot of customers coming to my shop, and I need to cluster them based on their spending patterns so I can decide which cluster to be marketed in what way. In that case, that is my supervised learning, unsupervised learning, because I'm not doing anything based on a class variable. I'm just looking at customers, how they spend, what they buy, and I'm grouping them into different groups. But I don't have anything to score my model based on. That is my unsupervised learning. Predictions versus classifications. This is a very interesting part. So in predictions, we have some standard accuracy metrics. Basically, if I'm predicting whether my sales are going to be good or not, I'm going to look at what I'm going to do is I'm going to split my data into train and test set, and I'll be training my model on the train set, which is typically 75% of my data. And on the remaining 25%, I'll test, and I'll look at accuracy, or I'll look at mean percentage error, and based on that, I'll see if my prediction is good or not. But when it comes to classification, it's a bit more trickier. In classification, let's assume that, for example, if I'm predicting whether the customer is at risk or not, I need to understand what is a cost of a false positive versus false negative to me. When I say cost of false positive or false negative, let's understand what that is, and it's a very important concept.
Bro,
If I
just press F5. Go to full screen mode. Press F5.
okay,
Thank you.
yeah. So in false positive versus false negative, let's understand what exactly a false positive and false negative is. I'm trying to predict the customers who are going to leave me. A false positive would be I predict a customer at risk, but that customer is actually not at risk. What could be the cause for me? I tried some marketing campaign on that customer. I give them some discounts. They were already not going to leave, but I'm giving them more discounts. That is a cost that occurs to me. Against a false negative, where a customer is not being marked as at risk, but then the customer leaves. In that case, I'm not giving any marketing or any discounts to that customer, but the customer has left me. So whatever purchases that customer could have made, that's my cost in this case. And in some cases, these costs are pretty much similar to each other, but there are some other cases. But there are some other cases in which false negatives are much at a higher cost than false positive. Now, if we have that difference between false positive and false negative, or if there is a class imbalance, a class imbalance is basically you have customers who have left you and you have customers who have not left you. But what if the number of customers who have left you is around 10,000 and the customers who have not left you is around 1,000? When there's a huge class imbalance like that, we generally choose precision recall over accuracy. That generally works well because what you have to optimize here on is the total cost that you're getting based on your false positive and false negative. For example, if your false positive is way costlier than false negative, you don't care about accuracy. You care about reducing your false positives. That way your cost is minimal. Second thing is some nuggets, like using logistic regression, we have to make sure that the data is linearly separable. If the data is not linearly separable, your logistic regression will never be correct. You will never be able to put it in a good use, and it will never give you right results. Because if it's not linearly separable, you might have to use something like SVM or something that can work with non-linear data and predict it well. And some things like if your data has more character variables than numeric variables, in that case, tree-based models work better because they work based on entropy and probabilities rather than something like a logistic regression that learns weights. Can you go on mute? Can you go on mute that?
कंटाळा म्हणजे त्याला प्रॅक्टिस नाही ना ती.
You're not on mute.
Oh, sorry.
Yeah. So let's go ahead with linear regression and understand what it is. So what are we trying to learn in linear regression? We have certain data, and we know that in X you have certain changes. X is basically your driver variables, the independent ones that driving your final variable. And you know that there's 1 unit difference in X, and you need to understand that what is that X is going to cause, that 1 unit difference in X is going to cause to your Y. Now, this is the simplest put way of a linear regression. But when you need to look at the real life scenario, you don't have one driver, you have n drivers. And every driver has their own coefficient of changing how your line switches. Now imagine the same thing if it's in a 3-dimension where you have x1 and x2. Instead of a line, you'll have a plane. In 4 dimensions, it's difficult to visualize it, but you get an idea of how that would look like. So let's look at a very simple demo, and then we can go to the next slide. So this is how the data looks like right now. If you see here, you have a variable called speed and you have a variable called distance. Based on what speed, how many distance was covered. That this is basically a standard data set in R. Once you install a ggplot2 library, you'll be able to find this particular data set. And if you do a quick check to see if your data is linear, you see that your data is fairly linear, but the variance it has from the line is pretty high. So anyway, if you try to predict this using a linear regression, it might have some error in it because since your data points are pretty scattered over there. So anyway, we can go ahead and check that if we can, first of all, apply linear regression on this. Now, once you plot your speed and your distance, you see that they both are fairly normal. The curve, the density curve that you see here is generally a bell curve like, and that basically tells you that yes, you have a normal distribution. Once you do that, you check if your speed and distance are correlated, and the correlation turned out to be 0.8, which is quite good. Anything above 0.6 or 0.7 would be considered okay. Now let's see, this is the model that we have. And once you run a model in R, this is the kind of summary it gives you. So let's pull it into a here, and I can show it here. So this was the formula that we did. We predicted distance. So distance was our y, and speed was the x over here. Suppose you had something more as time. All you had to do was do a plus here, add that second variable, plus, and add any number of variables that you want here, and it will consider all of those. Your residuals and coefficients that you see are over here. Intercept is basically your B0, which was this. That's your intercept. And speed is your another variable, and this is the coefficient for that. The standard error is 0.4, which is fine, and your P is pretty low. So this value tells that the variable that you use to predict your Y, whether that was significant or not. And 1.49 into 10 raised to minus 12 is as close as 0 as it can get, which basically means that your variable was pretty significant over here. After that, your residual standard error was around 15.38, and your multiple R squared was 0.6511, which is not really very great. A multiple R squared value should at least be around 0.8 or 0.9 for a model to be considered good. Now let's understand what happened with our model exactly over here. Let's try to do a training and test split to see if the model really works. So what we did here is basically first we did a 80-20 split on our model to get training and test data separated. Once we have our training and test data split ready, we can actually build the model. And once the model is built, we can use the predict method to predict for the test one, the 20% that we had kept aside. And once that's done, your actual prediction and models would look like this. This is something what it will look like, that the actual was this and the predicted value was this. You can see it's way off from the actual. Whether it should have predicted 2, it has predicted -5. Where it should have predicted 22, it has predicted around 7. I'll come to that, why is it happening, but let's see what the MAPE is. And the MAPE over here, that stands for mean average percentage error, is around 0.69, which is again pretty high. 69% error is basically something that you really don't want. Does anyone want to have a shot at why this would have happened? Any idea, guys? Okay, let me answer that. What happened here is basically when you run the model saw that in the training set, for one particular, in the test set, for the one particular y, we had 3 different values of x. And the same thing, but it could predict only one value for one value of x. That is where the data went wrong. What this particular thing means is that if for one particular x you have multiple values of y, that means there is some data that's missing. There's something that's missing in the puzzle, and your model is not able to figure that out. And obviously, because for one particular x, if you have multiple values of y, that means there is something else that's driving that y. And until and unless we figure out that piece, which could be anything else, any other piece of data, maybe time, maybe something else, we will not be able to understand the entire fit of the data. So that's one very particular thing about your model. This is where the business understanding of your entire domain comes in the picture. Now, why am I stressing so much on what is to be considered in a linear regression and what is to be not considered? So let's look at here. This slide basically talks about all the checks and balances we need to do before we go ahead with a linear regression. One very important thing, that there must be a linear relation between your independent variables, which is what we checked in the very first step to see if the data could be linearly fit, and we saw that the data was very scattered around the line. So this is your first step. Second is homoscedasticity. An example for this I'll show you, but right now let me tell you what homoscedasticity means. Basically, the variance of your residues, right? Once you predict a y based on an x, whatever residues that you get, that variance should be common across all your different samples taken of x. There's a standard test called Brosh-Pagan. Wait this again. Standard test called Brosh-Pagan test that you can take to understand if your data has homoscedasticity or not. But even before taking the test, I'll show you a very easy way of figuring out whether the data has homoscedasticity or not. So let's look at this particular data. This one. This is to check for homoscedasticity. So looks like there is a very normal, linear relationship between your data. So let's look at the summary. It looks like your variable was pretty significant enough, and then you do a plot of your residues. So when you plot the residues of your linear regression model and you see a standard pattern, over here you can clearly see that there is a standard pattern between your residues. It follows a parabolic path. And whenever something like this happens, that means your data has heteroscedasticity and you have to fix for it. And the fix for heteroscedasticity is pretty simple. What you have to do is you have to either use a log, or you have to add a new variable and add a square or some transformation of one of your variable, and that removes the heteroscedasticity pretty easily. So if you want to do that, what you can do is run this, and you can clearly see that now the parabolic path that you saw before, this was the parabolic path that you saw before, and now you see this. So that a particular pattern that you had seen before, that pattern has disappeared, and you have seen that your residues have become completely random. And this means your data has homoscedasticity, which is needed, and this means your data has heteroscedasticity, which means this needs to be treated. So I hope this is clear on homoscedasticity. Next topic is autocorrelation. I couldn't include an example on this, but autocorrelation is basically when there is a time dependency on your data. For example, if you had a business which had been running for years, since 2010, probably you had a business and it has been going well, and your business has been growing consistently over time. Now, what happens is when your business grows consistently over time, what's normal for you, what's mean for you also changes, and that mean goes with time, increases or decreases with time. And when the time dependency comes in your data, you cannot use a normal linear regression for that. You have to somewhere compensate for that times impact on your data. That is where you have to either use panel data regression or time series forecasting. And how do you know that? Again, there are standard tests called Durbin-Watson test or Yule-Walker test, and you don't really have to do a lot for this. There are standard packages available to administer these tests and give you the results. And it will be exactly as similar as hypothesis testing that I spoke of in the first part. The hypothesis for Durbin-Watson test is that basically your data has autocorrelation. If your probability is low enough of the null hypothesis, you can reject the null hypothesis. Same goes for Brosh-Pagan test. It picks up a null hypothesis that your data has heteroscedasticity, and if the null hypothesis is rejected, that means you don't have to worry about it. Independence is generally an assumption. Independence means that if you have 20 records, or if you have 2,000 observations, if you have 20,000 observations, it just means that every observation is independent of each other. As long as every observation is independent of each other, that means that it's good to go ahead with linear regression. Normality. X and Y are normally distributed. As I discussed before, we checked the density curves and made sure that your X and your Y are normally distributed, and then only go ahead with linear regression, always. Multicollinearity. What multicollinearity means is if you have 10 or 12 different, 10 or 12 different factors in your data, and each of those are not independent. For example, as I spoke, right, you have age and work experience as two different factors in your data, and they are generally going to be correlated to each other because the people who are higher in age will generally be higher in work experience as well. So these kind of factors generally cause problems for you. And how do you look out for them is you can either do a correlation plot in R and check if they are actually correlated, or there's a metric called variance inflation, which you can look at, which is readily available and see, or you can look at the variable significance. Generally, what will happen is out of 5, if 2 are multicollinear, you will see that only one of them is a significant and the other is not significant. And that is a catch for you. If you see that, you can literally drop the not significant one and run the model again. So let's have a look at that as well. And before that, I have another important concept to cover, which we can now look at, is bias variance. Now let's understand how this works. Every model that you apply is always going to have some error. No model is going to be 100% perfect. And that is where the concept of bias and variance comes in. Now, why we need bias and variance? Because once you have, so bias is basically your average of your predicted variable. So H bar is average of your predicted Y minus your actual Y. And your variance is your summation over Y minus H bar, which is your Y, for each Y you do the variance into K minus 1. So these two are necessary because your error that you get in any particular of your model is generally calculated as bias square plus variance, and whatever remains out of these two is considered noise. That is your unremovable error. Now, why talking of bias and variance was important? Because we always talk about overfitting or underfitting. We talk the model is overfitting, the model is underfitting, or it's not a good fit. It's basically your bias and variance. When your model has a huge variance, that is where basically your model is overfitting. What it's trying to do is it's trying to remember your data. If you see here, your model is literally trying to touch every data point that you have, and that is where it's going wrong because it's trying to memorize the data that you have. So in case of overfitting, when you're trying on your train set, you're going to get amazing accuracy. But anytime the model looks at some kind of a data point that it hasn't seen before, it's not going to perform well over there. Then what happens in case of underfitting? Your model generalizes too much and it's not able to capture the pattern at all. So this is equally going to be bad for you because again, as it sees a data point that that's not on its generalization curve, it's not going to predict it better. And a good balance is something where your most of your data point is near your model fit, and your MAP that you talk of, your mean average percentage error, that's minimum as minimum as possible. That is where talking of bias and variance is very important, because once you know that your model is overfitting or underfitting, first of all, if that's happening or not, bias and variance is a very good way of knowing exactly what problem's happening. And once you know whether it's overfitting, then you can apply some ensembles. For example, if it's overfitting, you can use an ensemble called bagging, and if it's underfitting, you can use boosting to fix your overfitting or underfitting problem. Then let's go and talk about if it's a regression model or if it's a linear model, and you need to know how good the model is. Or rather than how good the model is, if you want to understand, you have multiple models and you have to understand which model is better. That is where you look at these traits in a model. Your R square or adjusted R square value. This is directly given by R to you. R gives you this value directly, and this value is something that's higher the better. So you generally pick the model with a higher R square. The F statistic, generally higher the better, because this F statistics that you have here, it tells you whether your model is significant or not. If this p-value is not as low as less than 0.05, you generally should not go ahead with that model, because that means your model is not significant. So this particular thing applies here as well. Next is your standard error, that is closer to 0, the better. Because obviously there is never going to be a residual standard error equal to 0, but as less it is, that better it is. Again, your T statistics is something going to be similar as F statistic. The only difference between T statistics and F statistics is that the F statistics talks about your entire model, while the T statistics tell you about your each independent variable. And your AI-CBIC is basically your area under the curve, generally your accuracy. MAP is your mean average percentage error, and RMSE is one of the very well-known root mean square error. This is one of the very well-known accuracy measure for a regression model. And this is, as we know, since it's an error, it's the lower the better. The min-max accuracy is again a standard measurement for your accuracy of your model, and since it's an accuracy metric, it's the higher the better. So you can generally stick to one of these in the regression. You don't have to worry about a cost of false positive or a cost of false negative here. So here in regression, your accuracy is generally a good way to go ahead with. Now, can throwing more data means better model? Let's look at this. Look at the two options. As we know that we had in first case, we only had age as a factor. And in the second case, we added a new factor, which says whether the person has sibling or not. And we are trying to predict the height of a person. Now, in this case, age sounded like a good model here, a good driver here, because since the age was a significant driver, we had a good F statistic. The p-value was pretty high. The p-value was pretty low, and the R square was pretty high. Once we added a new variable called no sibling, now it's clearly a thing of common sense, right? Like with age, the height increases till a certain age. Between 0 to 18, the height increases for a person, and then the height remains the same. But there is some directional evidence between age and height. But having a sibling or not, it really doesn't have any impact on your height. So that is exactly that we're trying to see here. we are not seeing sibling as a significant variable. The p-value of the model has increased, which is a bad thing, and the F statistic has decreased. So that clearly says that adding an extra variable actually deteriorated your model. And that's what I'm trying to tell you here. You need to be very considerate about which variables you pick for the model, because throwing wrong variables at the model is going to create problems for you instead of making it better. And the last thing is, do we stop at R-square? So this is the same data that I had showed you before for heteroscedasticity. As you see, for the model that had heteroscedasticity that we had to fix for had an actual R-square value of 0.902. And generally, when people have a value of R-squared value of 0.902, they tend to stop thinking it's a good model. But when we fixed the heteroscedasticity and made sure that the model is homoscedastic, we saw that the R-square was almost around 1, and the residual plot was as required. So this is what we need to look at when we need to know, when we need to get the best estimates from the model. And that's why you cannot just look at R-square or any one of the metric, and you have to look at you have to look through all of these checks and balances before you go ahead and create a model. So that's all I have about the linear regression model, and I'll open the session for questions now.
Yeah, anybody has any questions on this topic? Anybody would like to ask anything?
Hello.
Although the session was very interesting. Yeah, go ahead.
Hello. Good
Yeah.
morning, sir. So my question is related to model. As you said at the time of you are discussing, no any one model is perfect. But my question is related to how exactly prediction are going to decide it, which basis, which model. There have any strategy either as which kind of model we will be perfectly used for the decision. The final decision is prediction.
So again, okay, first of all, please don't call me sir. I'm way younger to you all.
Yes.
And second thing is, you will never know which model is going to be better unless
Yes.
you actually build the model. So what we do is we generally have a, as I said right earlier, you in exploratory data analysis, right? Let me pull that one up for you. I actually did not get enough time to look at this.
Yes, yes,
so let
exactly.
me answer your question. Let me answer your question here. This is the data set that we're looking at. Suppose we have a data set like this, where we have information about diamonds. A diamond has a certain carat, a certain cut, a certain color, certain clarities, depth, a lot of things. And then there's a certain price for the diamond.
Yes.
Now, how I generally approach this question is, I'll first see how the price varies. Now, here I see that, okay, this data is very skewed. That means that for price under 5,000, I have a lot of data points. And over that, I don't have a lot of good data points here.
Yes.
So then I might go and see that is there any kind of a dip. For example, I saw this and I see that there's a certain dip at 1500, and overall the model looks good. I mean, overall the data looks good. So in this case, right, now I know that a linear regression model might not work good for this.
Yes.
Because
Yes.
when I checked this, the data was extremely skewed and nowhere near normal. So now this was one clue that linear regression is not going to work. Then what? I either have to use something like a tree-based regression or a logistic regression, but not for classification, a logistic regression model. So these kind of nuggets, that small nuggets that you get through EDA, you can get these nuggets to build your models, but that model is not going to always fit. Suppose it doesn't fit, you might have to try some different flavors that we call. So that's a common word that we call in models. You have to try different flavors or different iterations of those models. And the trial and error keeps going on till you get the accuracy that you deserve.
Okay.
And in some cases, again, it depends on your business case. In some cases, 80% accuracy is good enough. In some cases, you have to have 95% accuracy. And based on what your requirements are, you keep on tweaking the model till you get what you need.
Okay.
And even after you deploy your model, right, it's not always like that. Once you deploy the model, you'll use it for ages. You
Exactly.
have
Exactly.
to you have to keep refreshing your model once in a while, and you have to keep tracking the progress to see whether your model is continuously doing good, and you have to keep doing tweaks in between, and those iterations have to go in. That's why the DevOps part of the entire modeling process is also very important.
Yes. Yes. Yes.
So does that
Exactly.
answer your question?
Okay. Thank you, sir. Thank you.
You're welcome. Anything else?
I think if no questions are there, then shall we end the session? If anybody has any other queries are there?
I think Reshma madam can give vote of
Yeah, I think Reshma madam can go ahead with the vote of thanks. Madam.
Okay, sir. Sir, it gives me immense pleasure to propose a vote of thanks to Mr. Atharva Terai, Senior Data Scientist at Research Wing, Adobe USA. He is also a junior college alumnus in our own college. Your hands-on explanation on statistic analysis and machine learning using R will definitely guide us in our journey to write a better research paper and explore this new horizon. I would also like to thank the management of Thakur College of Science and Commerce, the ever-inspiring principal, Madam Dr. Siti Chakravarti, IQAC head of computer department, and this particular faculty development program coordinator, Girish Tere sir, for providing us with interactions with good speakers who have encouraged us to look into this new research areas using R and Python. Lastly, I would also like to thank all the participants for attending all the sessions. And of course, best of luck to all the participants to achieve the completion certificate of IIT Spoken Tutorial on R. Thank you.
You're
Thank you
welcome.
all.
Thank you.
Good day.
Thank you, Atharva. Have a good day.
You do.
Thank you.
Thank you,
Okay.
sir.
Thank you.